In this video, we're going to study a third primitive called coin flipping, or sometimes coin tossing, which is interesting first because it's useful in cryptographic contexts, and also because for that primitive there's going to be an advantage to protocols that use quantum information over purely classical protocols. So what's coin flipping? Here's the task. Neither Alice or Bob have an input, there's no inputs, and their goal after communication is to output the same bit C such that C is as close as possible to a uniformly random bit. So they want the same bit, and the probability that this bit is 0 should be half, same as the probability that the bit is equal to 1. So note that this primitive doesn't quite fit into the framework of multi-party computation that we've seen so far, because there's no input to the players. This is something we could allow before, except if there's no input, it means that the output would have to be fully determined. Whereas here we're considering the case of a randomized output. And what this means, to be positive about it, is that the impossibility theorems that we saw for multi-party computation don't quite apply. So it could be that this primitive can be implemented perfectly using quantum information. So now what does it mean to implement it perfectly? It depends what kind of security we require. So there's two standard notions of coin flipping. The first one is called strong coin flipping. The protocol will be a strong coin flipping protocol if it is the case that no malicious party, neither Alice nor Bob, can force an outcome C that is such that either the probability that C is 0 or the probability that C is 1 would be strictly larger than a half. That's what you would say is the natural notion of a secure protocol. You can define the bias of such a protocol, which would be how much above a half you can potentially bias the bit. Ideally, you'd have a bias of 0, which means that if just Alice or just Bob is dishonest, they can't force a 0 nor a 1 with probability bigger than a half. Now, there's a slightly weaker notion of coin flipping called weak coin flipping, and here we assume that each of the parties a priori is going to try to bias the coin in a certain direction. So for example, Alice always wants to get a 0 and Bob always wants to get a 1. And the protocol will be a weak coin flipping protocol if whenever Bob is honest and Alice tries to force a 0, she can't do so with probability larger than a half. And if Alice is honest and Bob is trying to force a 1, he cannot do this with probability bigger than a half. Again, you can define the bias of weak coin flipping protocol, which would be the largest epsilon such that this is possible. And then we'll talk about epsilon biased coin flipping protocols. So that's the goal that we're set to achieve. And the question is, can you do strong coin flipping? Can you do weak coin flipping? First, let's think about it just classically. This is a primitive that was first introduced by Bloom, and he called it coin tossing over the phone. So can you achieve coin tossing over a classical phone? Well, it turns out that unfortunately you can't in a very strong sense. So not only strong coin flipping, but even weak coin flipping is impossible, in the sense that as long as Alice cannot completely force a 0, then Bob can completely force a 1. Meaning there's always at least one of the two parties who, by behaving maliciously, can force their preferred outcome with certainty. So that's very unfortunate. It means that we really can't achieve anything in the classical world. The proof of this I'm not going to give to you, but the idea is to use that the outcome C has to be determined by the transcript. So if you look at the whole protocol and the whole communication that is exchanged, at some point the outcome C is going to be determined because it's determined at the last step. You can always imagine add a couple messages, and at the last step have Alice say to Bob and Bob say to Alice what their outcome is going to be. So the outcome is the deterministic function of the transcript. And then the question is, when did this outcome get decided? Which message was first such that the outcome was fully decided? And if it's a message that was sent from Alice to Bob, then it means that Alice has control. If it's a message that was sent from Bob to Alice, then Bob has control. So that's not a full proof, but it gives you the idea of how we're going to prove, one could prove this impossibility result. Okay, so no classical protocol for weak or strong coin flipping. How about quantum protocols now? So in the quantum case, it turns out that luckily we can do better. Again, there is no perfect strong or weak quantum coin flipping protocol. And the intuition for this is the same that was behind the impossibility results that we saw for oblivious transfer and bit commitment. The idea is that someone has to hold the purification of the whole system, and if, from the point of view of Alice, the reduced density is, say, totally mixed, because she's going to output a uniformly random bit, then Bob holds a purification, and Bob should be able to shift the outcome from 0 to 1. So using these kind of ideas, you can show that there is no perfect protocol, weak or strong, for coin flipping quantumly, but allowing a little bit bias, we can do better. So for the case of strong coin flipping, there's a bound which says that Alice and Bob will always be able to cheat to some extent, to the extent that either of them can force one outcome at least with probability at least 1 by root 2, which is larger than a half, right? This is approximately 0.71, which means that the bias should be at least roughly 0.2. That's for strong coin flipping. Now, weak coin flipping, it turns out that you can do any bias as small as you want, but not 0. Can't achieve perfect weak coin flipping, as I mentioned before, and here the downside is that the protocols that we know in order to achieve this have a number of rounds of communication required that grows very quickly as epsilon goes to 0. And in fact, it's known that if you want to achieve an arbitrarily small bias, you need a number of rounds that goes to infinity as epsilon goes to 0. It needs to be at least omega of log 1 by epsilon. This is slowly growing, but it has to grow. And what is known is that once you've achieved weak coin flipping protocols of arbitrarily low bias, which we know how to do, but it's a very complicated construction, it involves lots of rounds of interaction, then we can achieve strong coin flipping with bias 1 by root 2 plus epsilon. So there's a reduction from the one to the other. So you can see a pretty strong quantum advantage here, especially for weak coin flipping. Classically, no non-trivial bias was possible. Quantumly, any small epsilon that we want, we can achieve. So now let me discuss the relationship between coin flipping and bit commitment that we discovered in the previous videos. In particular, I'd like to give you the simplest protocol for coin flipping that's known, but it relies on commitments. So you can show that if you have a bit commitment protocol, which of course we don't have, but let's imagine for a second, then you could create a perfect strong coin flipping protocol. How would you do it? Well, here's an initial idea for a coin flipping protocol. Alice would choose a random A in 0, 1, random bit, send it to Bob, and Bob would choose a random bit B in 0, 1 and send it to Alice. And then both of them would output the parity of the two bits. In this way, they each kind of have a share in the output. And as long as either A is random or B is random, then the output will be uniformly random. So it seems that no one can cheat. Maybe they can, right? The problem is that Bob here in this protocol gets to choose his bit B after having seen A. So he can force any C that he wants simply by setting B equals to A plus C. So this protocol is secure against malicious Alice, but completely insecure against malicious Bob. How do you fix it? The idea is to use commitments. We want Bob to prove to Alice, certified guarantee to her, before receiving her bit, that he already set his mind on a certain bit B. But of course he shouldn't reveal B to Alice, because otherwise she could have the same kind of malicious strategy that we just described for Bob. So here's a strong coin flipping protocol based on commitments. In the first step, Bob would commit to a random B using the bit commitment protocol. In the second step, Alice would just send a random A, and then Bob would open B, and they would output C to be the parity of A and B. So you can check that if the bit commitment protocol satisfies the conditions of being perfectly binding and perfectly hiding that we learned about, then this protocol is a perfect strong coin flipping protocol with zero bias. So that's a nice reduction, it works very well. How about the other direction? There it's more tricky, but it turns out that you can use weak coin flipping in order to get improved weak bit commitment procedure. So now, as I told you before, we can achieve coin flipping, weak coin flipping with arbitrarily small bias. So this is something that is possible using quantum information, but not classical. We also know that perfect bit commitment is not possible. So you couldn't show that weak coin flipping implies perfect bit commitment, but it implies a better bit commitment protocol. Let me just give you briefly the idea. So here's an idea for a bit commitment protocol using quantum information. What Alice would do in order to commit to a bit B is that she would prepare the following entangled state, phi B, which is equal to 1 by root 2. She hides her bit here in superposition with a 2. So this is a 2 qubit state, and she sends over the second qubit to Bob. So this one and this one. That's the commit phase. And then in the open phase, she just sends B and the remaining qubit of phi B. So is this secure? Well, it's partially secure. First, what you can see is that the probability that Bob is able to guess B from his information at the end of the commit phase is at most 3/4. So at least it's not 1. We'd want it to be a half, but it's 3/4, between a half and 1. In order to show this, it's sufficient to compute the reduced densities on Bob's system when the bit B is a 0 or the bit B is a 1. So if you look at ρ 0 and you look at ρ 1, you can see that the trace distance between these two density matrices is a half. And by Hellström's theorem, we know that it means that the best distinguishing probability that Bob has between these two states is a half plus a half divided by 2, which will give us 3/4. So that's for the analysis against malicious Bob. The analysis against malicious Alice is a bit more complicated, because there you need to consider all possible states that she could prepare instead of phi B. In particular, she can prepare a superposition of phi B with some additional registers that she keeps to herself and on which she acts in order to open a different bit than the one that she committed to. So you can do this analysis, and again you can show that the maximum probability with which Alice can cheat is 3/4. So this is a valid protocol for bit commitment that has bias 1/4. And it doesn't use any coin flipping. So what's the point? The point is that you can improve this protocol to one that is provably optimal, that has a slightly smaller bias. Instead of 1/4, it's 0.21. So 0.21 instead of 0.25, that's not a huge improvement, but what's nice about it is that it's optimal. You can show that that's the best you can do. And for this, you use the weak coin flipping protocol in order to remove a little bit of power from Bob. So what you do is you increase the amplitude of phi B on 2, so you add something here that's a bit bigger than 1, which means that you also decrease the amplitude here. That's giving more power to Alice, but then you use the weak coin flipping protocol in order to make sure that Alice in fact doesn't have an increased power. And then it's a lot of fine-tuning of parameters, so I won't give you all the details. So to conclude, coin flipping is one of these really interesting primitives because there's a quantum advantage. And it's not yet known how powerful, how far this advantage can take us. And so the field is open to yourselves. Imagine that I give you a quantum coin flipping procedure with arbitrarily small bias. What kind of interesting protocols could you use this for?